All right, since that demonstration was pretty quick, let's try another example. This time, let's take a look at a 6-lead motor. You'll recall 6-lead motors consist of 3 individual windings: windings 1-4, winding 2-5, and winding 3-6, isolated from one another with both terminals of each winding externally accessible. When configured as a Y, terminals 4, 5, and 6 are tied together, and primary voltage L1, L2, and L3 is connected to terminals 1, 2, and 3, where swapping any 2 applied phase sequences reverses rotational direction. Alternatively, when configured as a delta, terminal 4 is tied together with 2, 5 is tied together with 3, and 6 is tied together with 1. Primary voltage L1, L2, and L3 is connected to conjoined terminals 1, 6, 2, 4, and 3, 5, where swapping any 2 applied phase sequences reverses rotational direction. Let's check out this 6-lead motor. When we pop open the pecker head, yes, this is a real term and I never grow tired of using it. Pecker head, pecker head, pecker head. A pecker head is a motor-mounted terminal box. When we pop open the pecker head, out follows a motor connection diagram unlike anything I've featured in the previous lectures. Rather than using the terminal numbers 1 through 6 as common in the US, it looks like winding U has ends U1 and U2, winding V has ends V1 and V2, and winding W has ends W1 and W2. This is most likely a motor intended for use in a different country with a functional government and affordable health care. Regardless of the terminal identification scheme employed, the motor connection diagram makes perfect sense. To make a Y configuration, ends U2, V2, and W2 are tied together to form a central Y. Primary lines L1, L2, and L3 would be applied to U1, V1, and W1, where swapping any 2 applied phase sequences would reverse rotational direction. Alternatively, to make a delta configuration, U2 is tied to V1, V2 is tied to W1, and W2 is tied back to U1. Primary lines L1, L2, and L3 would be applied to conjoined terminals U1, W2, V1, U2, and W1, V2, where swapping any 2 applied phase sequences would reverse rotational direction. As previously, let's use an ohm meter to check each winding. Again, normally 3-phase AC motors are considered balanced loads. Unless damaged, each winding should theoretically have the same resistance. An ohm meter demonstrates winding U from U1 to U2 has a resistance of roughly 41 ohms. Similarly, an ohm meter demonstrates winding V also has a resistance of roughly 41 ohms. And finally, an ohm meter demonstrates winding W also has a resistance of roughly 41 ohms. Looks like these 3 windings are indeed roughly identical. Inside the pecker head, we find 3 voltage clips. Let's use the connection diagram to set this 6-lead motor up in a Y configuration by tying together U2, V2, and W2. An ohm meter between terminal U1 and V1 sees winding U and V in series. The ohm meter sees a resistance of roughly 82 ohms, which is consistent with the series combination of 2 identical 41 ohm windings. Similarly, an ohm meter between terminals V1 and W1 sees winding V and W in series. As previously, the ohm meter sees a resistance of roughly 82 ohms, which is consistent with a series combination of 2 identical 41 ohm windings. Finally, an ohm meter between terminal W1 and U1 sees winding W and U in series. As previously, the ohm meter sees a resistance of roughly 82 ohms, which is again consistent with a series combination of 2 identical 41 ohm windings. I've got a reasonable degree of confidence we've placed this motor in a Y configuration. Let's do the same thing for a delta. The connection diagram specifies U2 be tied to V1, V2 to W1, and W2 back to U1. An ohm meter between conjoined terminals U1, W2 and U2, V1 sees winding U in parallel with a series combination of V and W. The ohm meter sees a resistance of roughly 28 ohms, which is consistent with a 41 ohm winding in parallel with an 82 ohm series combination of 2 41 ohm windings. Similarly, an ohm meter between conjoined terminals V1, U2 and W1, V2 sees winding V in parallel with a series combination of U and W. The ohm meter sees a resistance of roughly 28 ohms, which is consistent with a 41 ohm winding in parallel with an 82 ohm series combination of 2 41 ohm windings. Finally, an ohm meter between conjoined terminals W1, V2 and U1, W2 sees winding W in parallel with a series combination of U and V. The ohm meter sees a resistance of roughly 28 ohms, which is again consistent with a 41 ohm winding in parallel with an 82 ohm series combination of 2 41 ohm windings. I've got a reasonable degree of confidence we've placed the 6-lead motor in a delta configuration. All right, that wasn't too hard, was it? In summary, follow the motor connection diagram exactly as directed. If you want confirmation, Use an ohmmeter to check your work. I should note that not all motor connection applications are as easy as these examples might imply. Each connection diagram was available and correct, and each wire label was present and legible. This is not always the case. Environmental contamination, old age, and just plain stupidity might wipe the numbers off the wires. In later lectures, I'll show you how to determine what wire goes where for unlabeled windings. Ironically enough, this technique necessitates the use of an old-school analog voltmeter, something you might have to scrounge for in a thrift store, junkyard, or grandpa's garage. Until then, this concludes this lecture. In conclusion, this lecture took a look at a couple motor connection examples. We set up a 9-lead Y-configured motor in the low-voltage YY configuration, and a 6-lead motor as a Y and again as a delta. Additionally, we used an ohmmeter to check our work. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.